So the push-pull stage, complementary, parallel, common source. So we start again with complementary parallel two ports. Then if we have CS stages, the minus is just one terminal, is a source terminal. So in both, so we have a P device and an N device of which the sources are connected, the gates are connected, and the drains are connected. So then it would look like this. And here is another way of drawing it. The gates are connected, the drains are connected, and the sources are connected. And like we did with the differential pair, we are going to look at the biased CS stage. And this is a little bit more complicated because probably you are not used to looking at the biasing like this, but maybe therefore it can also be very helpful. So here we have biased it. And you see immediately, as we saw with a two-terminal network, that IG of one device eats the other one. So externally, there's no IG observed, of course. And IDS also. You can leave them out and because they don't add anything, and the device is completely biased with voltage sources, as the differential pair was completely biased with current sources. So here we have shifted the VDS through the device, which means if you shift it through the device, so it enters in the source and it also enters in the gate. And that's what we have done. So then you get this circuit, and now you see a positive and a negative power supply, and the voltage VGS was minus because you look at the orientation, yes, because we now have the source drawn on top of the P device, and of the N device we have it on the bottom. And so we have to shift VDS to it, so we obtain VDS minus VGS as bias sources here. This is basically the way of biasing, and a common mode current is not observable, of course, and doesn't need to be applied. It's just a result of the voltages applied and the device characteristics, as it was for the common mode voltages of the differential pair. So we are also going to look at the VI transfer, and then the name push-pull stage will become more clear. So we have seen a few lectures ago that we can find the operating the input offset sources, the input bias sources, by applying the output bias sources, creating a loop with a voltage controlled voltage source, and then measuring the voltage at the gate. And for this MOS device, the gate current will be 0. So we only have to read this VGS. And this is a P device, so it looks a little bit different than for the N device. The whole thing is flipped, but of course, the principle is exactly the same. So here the operating current IDS is IQ, and the voltage that we want to operate is VP. Now here we have the N device, and that is, let's say, what you hopefully recognize from the previous lecture. Here we have IQ also, and we have an operating voltage Vn there, and we find the negative, the gate voltage required to get this operating point in the device. So node 4 and node 2 will approximately be 0 volt. That is the aim of the biasing. If we have VGSP and VGSN, and we remember the previous sheet, so we have the VGS, we can make this circuit, apply VP and VN as power supply, and add VGS as a floating voltage source that we derive with the gain of unity from our model. And this is the model-based biasing effect. So here you see, here is my E3 and E4 are two voltage controlled voltage sources with a gain of unity. They measure the gate source voltage of the P and the N device, and they copy it in series with VP or VN. And now the whole thing is biased, as has been described before, and there is 0 at the input, and I can connect a DC voltage there to sweep the voltage at the input and measure the short circuit current exactly as I did in the differential pair. But now I have one current, so the current of one minus the current of the other is just the current in this node. And in the LT-SPICE, you put there a voltage source and you measure the current through it, and we can plot the voltage to current relation of this uh, system, of this stage. And here you see I plot it as a function of the quiescent current. And again, they are not in order. You see 100 nano, 10 nano, 10 micro, 1 micro. It's a little bit messy here. The smallest one is 10 nano, the blue one. The blue one with a large dead zone. So I have a very low quiescent current here. And the highest current is the 10 microamps. You see here, IQ of 10 microamps. The green one, which is an overlap of the two stages. And you see now, let's look at the curve. Let's look at the thing, the blue one, which is biased at 10 nanoamps. 10 nanoamps, but it can deliver, there is microamps along the scale here. So it can deliver up to, well, roughly, but like 80 microamps positive and 80 microamps negative. Of course, the devices are scaled so that it just looks like more or less the same, and the ratio is about 4. It's a little bit less, about 3.5, because of the mobility of the holes and the electrons, which is different, and therefore the P devices need a wider to be wider than the N devices. So here you see the output current as a function of the voltage, and you see it can deliver much more current than its operating current, and that's why we call it a push-pull device, because basically one device delivers the source current, and the other does the sink current. Now, I unfortunately placed this arrow of IO from the ground to the drains, which means that it is not that source and sink and push and pull is a little bit messy, but the upper device, the P device, is sourcing, is delivering a positive current to the load. Here, a negative current, of course. And the other device, the N device, is sinking. It is taking a current from the load. You could say it in this way. So we have a source device and a sink device. Pushing is when the current flows from the output of the stage through the load to the ground. Pulling is when it is the other way around. And now we can define all the names later on. So first, we have exactly the same even function for the common mode. And the common mode is now the sum of the currents through the devices, not the difference that is flowing here through the output, IO. No, the sum of the two currents is now the common mode current. They seldom call it the common mode current, but if you are really strict in the naming, then you should call this the common mode current. And again, you see the even characteristic here. I explained already the pushing and the pulling. So class A operation is when the sink and the source devices, so in this case the P and the N devices, conduct during push and pull. It means that your bias current is larger than your signal current, basically, in both phases. Class B is when the sink device conducts for pull and the source device conducts during push. So it would say 1/2 of, let's say the positive half is done by one device, and the negative half is done by another device. Well, it means that there is an exact takeover. And you see already in this curve that that is not possible. Smoothly, the conduction of one device goes into the conduction of the other device. That's why almost all stages are then class AB. There's an overlap. And you see a lot of overlap in the green one, because then when they both operate, you have more gain. That is the factor 2 we have talked about in the, because it's BS, it's voltage to current, the factor 2 in the gain that we get if both devices are in the same operating point. So there's overlap. If there's no overlap, so take the blue one, is there even a dead zone? We speak, well, one is conducting in the positive half and one is in the negative, and then there's a dead zone, and we call it class C operation. So that is important to understand what these names are about. Of course, in class C, there's a huge distortion, but for RF amplifiers, it can be a very nice way of operating because the harmonics generated are not part of the band that we are interested. So we can filter them out. So if you have a small bandwidth, you are only interested in a small bandwidth, you can allow distortion as long as, of course, as long as there's no intermodulation distortion, but you could allow distortion and then your resonator will filter out all the harmonics that you are not interested in. So this is the large signal static transfer of the stage. And again, this whole circuit, there's a link on the website to the LT .cir file, and you can plot the curves yourself. These curves are not plotted with LT-Spice, they are plotted with Symmetrics and with Python. Unfortunately, I didn't sort the currents. That's what I should have done before, but okay. The small signal transfer. So let's study, as we did with the differential pair, the behavioral modifications resulting from anti-parallel connection or parallel connection, because small signal, linearized, there's no difference between parallel and anti-parallel. So here we have it. We have, again, the two ports and the transmission one matrix. That is our favorite method of representing amplifiers, the two-port parameters. And now we see that we have not B doubled, but we have half the value. So the gain from voltage to current is doubled. And that is what we have seen in the previous picture, because this is 1 over the transadmittance. And C is doubled. So we can apply this, of course, simply to the diagram. Here we have the diagram of the two devices. They're just in parallel, so you add all the components. You just put them in parallel. And if you are in the quiescent operating point, you can simply multiply the whole thing with 2. So this is the small signal equivalent circuit in the operating point. Next step is the noise. And, well, probably you are already suspicious that there will be something like we had with the differential pair, that the representation is not so handy. So here we are also going to study behavioral modifications resulting from anti-parallel connection of linear two ports, and here we have them. And now the point is what to do with this V. If you shift Vn through the node, it will end Vn2, it will end in series with Vn1 and with the input, and you will never get them both at the input. So that is not the way to go. But as we did with the differential pair with anti-series connection, we said, no, if we have a series connection, then you can add voltages. That is much more easy. So if we have parallel connection, we can add currents. So we need another model. We need a model in which the noise is represented with 2 current sources. And as you know, hopefully from the previous course, the bachelor course, we have 6 representation methods for noise of 2 ports, for noisy 2 ports. We can do V and I at the input, what we want for design purposes. But for analysis purposes like this is not very handy at all. Here we want to have two current sources. So we go to two current sources. We convert the model, and then V is converted into two correlated currents, one in parallel with the input and one in parallel with the output. And then you use the ABCD of the total constellation, of the total thing, to bring the current sources from the output back to the input. And we have exactly the dual situation. Now we have half the voltage plus half the voltage of the other one, and which means that the spectrum is 1/4 times the sum of the two spectra of the voltage. Yes, the current is a sum of the two spectra. And that means there's no costs. Let's say it's like you have a CS stage, but now you have two transistors, and the width can be 2 times smaller, and the current can be 2 times smaller. The operating current to have the same. But unfortunately, so this is the conclusion, but unfortunately, we have no ideal complementary devices. So PMOS and NMOS are different. They are not fully complementary, and about a factor of 3.5 to 4 is the mobility, the carrier mobility in the PMOS is about a factor of 4 times lower than in the NMOS, which means that the above rule is not valid. You need much more space if you do it in area, if you do it in this way. So the advantage of this stage basically is the push-pull characteristic, having a low operating current and the ability to get a current out of the device that is much higher than the operating current. That is good for the power efficiency of the amplifier, and that is why class AB stages are often used at output stages in amplifiers. The price is that there is a nonlinear region that you have to take care of. This is called the crossover region, where one transistor takes over from the other region, but maybe we can deal with that. And if you can, you have a high efficiency output stage. There's also a slide gap model. And it's just one symbol because it's a P and an N in parallel, and it's a small signal model, but there are two devices in it and are just placed in parallel. So in red, you see the width, the length, and the drain current for the N device, so subscript N, and in green, you see the parameters for the width, the length, and the current of the P device. The model that you have to, the symbol that you have to place in slide gap is SL from slide gap, X from subcircuit, M from MOSFET, and PN from there's both a P and an N device in it. And the subcircuit that has that accepts these parameters and calculates the small signal equivalent model parameters for you from these parameters is CMOS 18 PN.